Hey guys, what's going on? So today we are going to be talking about the Ricci tensor. This is we're getting to a point in tensor calculus where we're going to start reaching into the higher echelons of more advanced areas of tensor calculus, and this is going to bleed over into general relativity. General relativity, though, I'm going to have a separate playlist on. I'm strictly trying to adhere to just the math part of tensor calculus. Anyways, we're going to be talking about the Ricci tensor. We're going to be talking about it sort of in its generality, and then we'll dive deeper into it later. So without further ado, make sure to hit that like and subscribe button. Make sure to go onto my Patreon page if you want to support this kind of content. And now let's get straight into the Ricci tensor. Okay, so we are talking about the Ricci tensor today. The Ricci tensor is, if we go back to this picture, right, so this was that sort of pyramid of space-time I talked about. For every point in space, we had vectors in the tangent space, and then we could also generate metrics that mimicked the effect of an inner product within these vector spaces. And we can define the connection coefficients in terms of our exterior geometry, right? Our exterior geometry again came from defining it in terms of these a mu vectors, or these vectors here just written out are arbitrary vectors, but they could be the velocity of some object at a point, or the acceleration. These vectors define the connection, right? The affine connection, which was torsion-free and metric compatible, in an exterior way. Likewise, the interior definition, or the not interior, right? The intrinsic. So we have the extrinsic and the intrinsic definition of the connection coefficient. What was a connection coefficient in terms of the metric tensor, and the metric tensor again was something that was at each point in space-time. So from the connection, we were then able to establish a covariant derivative. Okay, and then we can take different routes here, right? So one route was to go about and define the Lie derivative, right? So from a covariant derivative, we were able to then talk about the Lie derivative, and then from the Lie derivative, we were able to talk about the torsion tensor, right? So this is torsion tensor, and sort of similarly, we also are able to get the Riemann curvature tensor, and the curvature and the torsion are two intrinsic properties to a surface or a curve that we can assign at each point, right? And it tells both of them tell us something about how an object rotates around a point, which is the torsion, and the curvature tells us something about how what exactly the curvature is like, or how it can be described at, again, this point. If we called it P, for example, we called this point P. The curvature tells us something about the curvature at the P, and the torsion tells us something about spin at P. Spin is sort of a loose term I'm using right now. We'll get into more of this later. So from the curvature tensor, we then can actually go about and define a ton of more tensors. The first one being the Ricci tensor, right? So the Ricci tensor is going to be what we're going to cover in the next few videos, okay? And then from here, we get into the more advanced stuff. So like the Weil tensor. The Weil tensor is going to be important for studying conformal transformations of space-time. And then from the Weil tensor, we can get, we'll take a look at the Schouten tensor and the Lanczos tensor. And then even from the Schouten tensor, we can get this Bach tensor, and we'll go more into this later. This is going to probably be a really deep dive into more advanced areas in tensor calculus, but interesting nonetheless. And from Ricci, we can also get the Plebanski tensor, which was the trace-free part of the Ricci tensor, and the Canton tensor which was a conformal, defined a sense of conformality. From the Ricci tensor, we can take the Ricci tensor and also define the Einstein tensor, but we're going to need to define the Einstein tensor. We actually need to define the scalar first, right? So the Ricci scalar, and then we take both the Ricci tensor and the Ricci scalar, and we define the Einstein tensor. Okay, the Einstein tensor. This is going to be more physics, right? Because Einstein himself dealt with physics, and that's probably going to be something reserved for a physics playlist. A lot of this here, however, we talk about conformality, we talk about generating Weyl tensors, we talk about the Kulkarni-Nomitsu product of the Schotten tensor being part of the Weyl tensor and all this kind of stuff. This is all math stuff, right? Conformal invariance, this is all mathematics. This is the kind of stuff we're going to go into a little bit deeper in this playlist. But we're at this point now where we're at this sort of crossroads. We're talking about the Ricci tensor and the Ricci scalar, and then we're going to talk about all this later. There's a couple of other things that we could also go down, which we're going to do. We're going to talk about variational tensor calculus. We're going to talk about forms. Forms are something. So once we finish with the Ricci tensor, we're going to dive straight into forms, okay? And that's going to help us understand things a little bit better also. And then we also want to talk about geodesic deviation. We want to talk about killing vectors and all that fun stuff as well. But let's get into the Ricci tensor. All right, so that was sort of a hint for what's to come. The Ricci tensor, so what we want to do here is we want to suppose that we have a vector acting at a point P, representing the velocity of an object. And so here's our vector, is V, we're calling it V, and suppose we could transport it this way by, with the representative vector here is U, so we're traveling in the U direction. In this case, we're traveling in the V direction by a small factor epsilon. So this epsilon is a small number, and so the constraint here is that, again, this here is small, so we're traversing a small distance. Okay, we want to know what the difference is in V as we travel between between both directions, and so we'll use the Riemann curvature tensor. We can use the Riemann curvature tensor, and we define this difference as the Riemann curvature tensor. These are all those necessary vectors. So we're in the U direction, the VK direction, right? So here's a V. The nomenclature here is a little bit weird because V is pointing in that direction, but it doesn't necessarily have to. But this is going to be, I've sort of named it VK for the video here. And then we have the VL. This is the actual vector itself, right? So this is this vector, this red vector right here. So maybe what I can do is I can do VL like that. So that L is summing over that L. All right. So we can define the acceleration then as the acceleration is the change in this vector, right? So and what we want to do is we can, if we divide both sides here, right? So divide both sides by epsilon, and then we take the limit of both sides, right? So that's what we're doing. We're taking the limit of this, which is equal to this right here. So the acceleration, again, is the derivative in that V. Again, VI is, I should put this in red, right? Because this is the, actually no, I don't want to put that in red because I depict that change right here, right? So that's this right here. And so we divide both sides by epsilon. We define this as the acceleration, and this is what we get. Okay? And then we get So if we get to the point here, if we're to divide again both sides by this e, then we get this right here, right? So divide this by e, and then, right, so those two guys will cancel, and we get this guy right here. We're just not showing this anymore. Okay. So now we want to sort of visualize this now as, suppose we have some circle, and we'll talk about this later. Here's that point P. Okay, and actually, no, the point P is the center of the circle, or the ellipsoid, and here's point Q. This is the picture we want to keep in mind here. This circle, and what's going to happen is we're going to have this circle sort of traverse these lines here. So if point P is right here, and point Q is right here, okay, what we're effectively doing is we're defining this as a radius, and so when we do that, we can define all of these right here. So depending on if this is a circle or an ellipse, we have all these radial distances labeled by I. Well, this is going to be some initial radius or some initial radial component of this circle plus 1/2 the acceleration times epsilon squared. Taking the temporal derivative, we get this. Taking the second derivative, we get this right here. All right, so we want to keep this in mind. We want to keep this in mind in particular, right? So the double derivative of the position of the radius is the acceleration, the acceleration of that radius. So when we have that in our minds now, we now want to consider what an object like this might look like. So this we said was the acceleration. This here we said was this. Okay? And we have all this, right? We have this here too, but E again, this is small, so we're regarding this as negligible. Okay? So we take this is equal to this. If we multiply and divide both sides by epsilon, what we get is this, right? We're doing nothing. We're multiplying and dividing both sides by epsilon. But then what we notice here is that we know what this is, right? We found out that was right here. All right. Well, if we know what that is, we just put that in right here. All right. So this is our Riemann curvature tensor. These are all the vectors that represent the directions we're traveling in, and VL represents the vector itself that's being transported. And then we have the radius and we have epsilon. So if the radius is small, again, the radius of this circle, again, this circle here, if this was epsilon and U is in a coordinate basis, right? So this is that direction U. The choice of the direction of U will contract with the Riemann tensor, right? So this right here is going to contract with the Riemann tensor, and what that means is we get something that looks like this, right? So these guys will cancel if we set this equal to, if we set the initial radius to be this small value, and we get this guy right here. All right, so we let's circle this, right? Let's circle this, or box it. Call that 1, equation 1, and we're going to put a hanger in that for a few minutes here, and we're going to talk about a sphere in n dimensions. we don't really need to think about this in n dimensions, but this is a general volume of a sphere in n dimensions. R is the radial dimension along each axis of that sphere. So you can plug, 3 into here, and we get your typical 3/4 pi r squared. That we for our volume if we're in 3 dimensions. But in its most general form, we have this. I'm not going to derive this, but we can actually take the derivative then, which looks like this, right? Because this is a product. We're doing the product rule, but then we need to divide by. The product rule is going to, for each element, right? So here I'll do it like this. For each, we have R1, its derivative times R2 times R3 plus R1 times R2 times R3 and so on. Well, we can divide, right? So we can, if we can multiply both sides by R1. Actually, for each one of these, right? So for each one of these guys, we can divide this by R1. All right, and we can multiply. Actually, here, I'll do it like this. I erased something important, right? Because this is probably an easier way to go about this. We're really kind of compensating here, right? Because we take, so there's going to be terms, R2, R3, and R1, right? So 1, 2, and 3. If we divide by R1, we effectively get rid of the R1s. And then if we multiply by the derivative of R1, we get this term. This is the first term in that product rule. So that's what we're doing right here. Right? So we're dividing by R1 and R1 down here, and then we're multiplying by that term, by 1, R1. So there's a sum and there's a product, and by doing this, this is a full fleshed out form of the product rule, essentially. All right, and then I won't go through the details on this. This is sort of complicated looking, but the whole point here is that this is the double derivative of the of this sort of ugly. I wouldn't say ugly, but this derivative of a volume of an ellipsoid in n dimensions. We do this, we take the derivative again, we get this, and if we again make these stipulations, if the initial velocity is 0, then this whole thing is going to go to 0. So we're making the stipulation that the initial velocity of the radius is 0, or the radial components is 0, and we get this guy left, right? This constant, again, this is just this up here, right? So all of this is the constant, so this constant. And we could see there's a few similarities here, right? There's this guy is the same as this guy, and we have something similar here. Effectively, what's going to happen is we're just going to get left with this guy. All right. And so what we get is this guy right here. And then we get, so we get this right here. And then we notice here, well, we defined this guy, right? We didn't really define it. We actually found out that it was all this right here. All right, so We put that in. We're summing over I. Right, so that's implied in the Einstein sum right here. And then we get implied in the Einstein sum. That's a contraction. Then this is the Ricci tensor. So the Ricci tensor, when it acts on this is the vector it's acting on. This is one direction that it's traveling. It's going to equal the ratio of the acceleration to the initial volume. So the acceleration of the volume to the initial volume. All right. Okay, well, we can divide. Suppose we divide both sides by this term here. And we get this right here. So the acceleration of the volume, right? So here's that volume. Here's the initial direction. These guys constitute the initial direction that the sphere is moving, right? Because again, these are directions, and this is these are vectors, right? These are vectors. This is a volume, and then this. We could talk about how this is I won't go too deep into this right now, but this is a volume. This is that initial direction, and this here is the Ricci tensor. All right, and so that's really what the Ricci tensor is, right? The Ricci tensor tells us something about the acceleration of a volume as we. This is the Ricci tensor. Tells us something about right up here. Ricci tensor tells us something about the acceleration of a sphere, right? Because remember, we're talking about a sphere here. This is that picture I had right here. We can imagine a sphere. Suppose, so here's point P, and here's point Q, and if our geodesics, say, look like this, we want to know, okay, if it travels in this direction, here's Q again, so there's our sphere. Oh, this is not a good drawing. But something like that, right? And then as here's Q again, right? Not Q, right? This we're traveling. We can do this again at this point. Suppose this was point P now, or we'll call it P prime, moves in the direction of the geodesic. And so we can imagine a sphere, the center of a sphere traveling along a geodesic, and its volume is fundamentally changing. It's accelerating, right? The acceleration of a volume as it travels along a geodesic is given to us by the Ricci tensor, right? So this is video 1 on the Ricci tensor. In the next video, we're going to go into it more, and we're also going to go into the Ricci scalar. Then once we hit the Ricci scalar, then we're going to put a pause on tensors for a second, and we're going to come down and we're going to talk about this stuff here. We might talk about the Weyl tensor. Also, the Weyl tensor is sort of the next big thing to talk about, and then we'll get into all of these different types of tensors as well. Right, and this is what's going to help. So there's a lot of videos out there already that talk about everything we've talked about so far. Right, they talk about the all this stuff up until we get to the Weyl tensor. There's a good video series by ZYLYX. I said Z, right? I think I'm not. X, Y, L, Y, X, Y, L, Y. I think that's how he puts it, Xylix, I think is what he calls himself. But this is a good YouTube channel if you want to also look into this stuff as well. His videos are a little bit longer because he doesn't pre-write stuff on his board, but very, very good, very, very good lecture series. But with that being said, I hope you like this kind of content. Again, make sure to hit that like and subscribe button and visit that Patreon page. And I will see you guys in the next video.